Hi students, today we're going to study about a special kind of standing waves. You see, we learnt in our last chapter that when waves get reflected, then standing waves are produced because the incident wave and the reflecting wave combine to form a special kind of wave which doesn't move, a standing wave. Today we're going to study standing waves in a variety of interesting situations. For example, what happens when we create standing waves in a string? What happens when we create standing waves in an organ pipe? What happens when we create standing waves in a resonance tube apparatus? And how can we use that to determine the speed of sound? We'll talk about things like that and more, of course. So let's begin. You see, when you're vibrating a string and the string is free to move at both ends, then any frequency can be used to generate standing waves in a string. You'll create an incident wave at a certain frequency, there'll be a reflected wave at a certain frequency, and a standing wave will be created. But when a string is bound like this, that is, on the left you fixed one end of the string, on the right you fix the other end of the string, then some restrictions crop up, because whatever wave will be formed will have to be formed such that this point is a node and this point is a node, right? Because this point will always be fixed and this point will always be fixed. So whatever wave form is formed in case of the standing wave will have to be such that both these points are nodes. So only certain frequencies will create waves which will create standing waves which will have this point and this point as the node. The natural frequencies of a string are those frequencies at which nodes are created at both the ends of the string by the standing wave that is formed by these frequencies. Again, this might seem complicated, but you'll get the hang of it very soon. So now, how can we vibrate the string so that nodes are created here and here? Like, what kind of standing waves can be created so that nodes are created here and here? Well, this could be one standing wave. Why not, right? This is an antinode with maximum amplitude. This is a node, this is a node. Similarly, even this pattern can be created. Right here. There will be a node here, a node here, and a node here. And this could be a standing wave. Then, this could be another pattern that could be created. A node here, a node here, a node here, and antinodes in between. But the primary condition in this case for a string fixed at two ends would be that there is a node at both the ends. As you can see, infinite such frequencies can exist for which standing waves can be created in a fixed string. The only condition is that there must be a node at the front end and a node at the rear end. Now, in the case when only one wave shape like this is created in the standing wave, the frequency required to create this one wave shape is called the fundamental frequency of the string. In this case, if you observe carefully, you'll see that the length L of the string is equal to lambda by 2. Why is that so? Because we had already studied in the previous chapter that the distance between two nodes is always lambda by 2, and so the distance here L is lambda by 2. That means lambda is 2L, or V by F is 2L because V equal to F lambda, and that means F is V by 2L. This frequency F, that is V by 2L, required to generate only one wave shape in the string is called the fundamental frequency of the string. It's also called the fundamental tone or the first harmonic. So the fundamental frequency in case of a fixed string is F equal to V by 2L. Now what will happen if you generate a wave shape like this, with two crests and two troughs? In this case, what will be lambda? The distance between this node here and this node here will be lambda by 2, and the distance between this node here and this node here will also be lambda by 2. So 2 into lambda by 2 is equal to the length of the string. That means lambda equal to L, or F equal to 2V by 2L. In this case, the frequency required to generate 3 nodes in total and one node in between is called the second harmonic or the first overtone. You will have to remember these terms because they are important. So in case of the fundamental frequency, we call the frequency the fundamental tone or the first harmonic. In the case when 3 notes are created, 2 notes already existing and 1 extra node, we call the frequency the first overtone or the second harmonic. Now what will happen if we create 3 such crests and troughs? Or what will happen when we create 2 notes in between? This will happen, right? This is the standing wave that will be created. In this case there is a node here, here, here and here. And as we already know, this distance will be lambda by 2. This distance will be lambda by 2 and this distance will also be lambda by 2. So lambda by 2, lambda by 2, lambda by 2 is 3 lambda by 2 equal to the length of the string. And clearly lambda is 2L by 3 or the frequency is 3V by 2L. So the frequency required to generate 4 notes in totality and 2 notes in between the fixed ends is called the third harmonic or the second overtone. Similarly, there can be a lot many harmonics and a lot many overtones. In fact, there can be infinite number of notes present in between these 2 notes and the frequency will keep on increasing. One interesting thing you must have observed by now is when we didn't have any node in between, but when we just had a loop like this, the frequency was V by 2L. When we had one node and we had 2 loops like this, then the frequency was 2V by 2L. And now when we have 3 loops like this, 1, 2, 3, with 2 nodes in between, the frequency is 3V by 2L. So for the nth harmonic, n lambda by 2 will be equal to L, because for the first harmonic, 1 lambda by 2 was equal to L. For the second harmonic, 2 lambda by 2 was L. For the third harmonic, we just saw that 3 lambda by 2 was L. For the fourth harmonic, 4 lambda by 2 will be equal to L. So for the nth harmonic, n lambda by 2 will be equal to L and the frequency will be equal to nV by 2L. So the frequency of vibration required to create n loop in a fixed string is nV by 2L. The frequency nV by 2L is called the nth harmonic. In case of the nth harmonic, n minus 1 nodes will be created, as we saw in this case. Third harmonic, 2 nodes were created. Second harmonic, 1 node was created. nV by 2L represents the allowed set of frequencies with which a standing wave in a string fixed at both ends can vibrate. That's clear enough. Now let's go a step further and understand the phenomenon of resonance in a string fixed at both ends. You see, if you set up vibrations and standing waves in a string, they die out after some time, they get damped because there is no driving force to generate the waves again. For example, you generate a wave from this end, it travels to this end, it comes back here, and the incident wave and the reflected wave combine to create a standing wave, but then these waves die down. However, if there is a driving force which keeps creating new incident waves, more incident waves from the left end, and like this, and then more reflected waves will come back, and then incident waves go, reflected waves come back, incident waves go, reflected waves come back, and then a sustained standing wave can be created. Now let us see what will happen if we actually provide such a driving force. Let us assume that there is a tuning fork here. This tuning fork is sounded very near this node, and when that is done, waves are generated in the string. Let this tuning fork be the driving force, and let the length of the string, for our better understanding, let the length of the string be such that L equal to n lambda by 2. That is, the length of the string is a multiple of lambda by 2. Lambda here is the wavelength of the waves created by this tuning fork. So L is n lambda by 2 and the tuning force is generating waves of a certain frequency here. When we do that, here waves like this will be created, which will travel from left to right, like this. This wave will be reflected by the fixed end here. It will get inverted and it will come back. It will get inverted here and come back right here to its initial position. Now at this stage, this wave which went here and which then came back has travelled a net distance equal to 2n into lambda by 2, right? Because L plus L is the distance it has travelled. That is, it has travelled a net distance equal to n lambda. So now there will be a new wave generated by this tuning fork at this instant, and the new wave that will be generated by this tuning fork at this instant will have a path difference of n lambda compared to this wave. That is, it will be n lambda behind this wave. Now we already know that if the path difference between two waves is n lambda, that means they will be in phase, and since these two waves will be in phase with each other, the resultant wave that will come out of this constructive interference will be something like this, a much bigger wave. Why? Because this wave which got reflected and got back was in phase with the new wave the tuning fork was sending, and the net wave that will be formed will be like this. Now this wave will again travel to the right, it will again get reflected and come back, and it will again get inverted like this. And again, since this wave has also travelled a distance of n lambda by 2 from left to right and n lambda by 2 from right to left, again it will be in phase with the next wave that is being generated by the tuning fork, and therefore this wave will interfere constructively with the new wave being generated because of its phase difference of n lambda with the new wave, and this wave will travel again. So as you can see, if the length of the string is equal to n lambda by 2, the phase difference between the reflected wave that has come back and the new wave generated by the tuning fork will always be n lambda, and therefore the standing wave created will be sustained. In fact, it will not just be sustained, it will keep increasing in amplitude because the waves will interfere constructively and the amplitudes will keep getting added. Such a situation where a driving force makes the amplitudes of the waves created in the string increase because the waves that are produced later are in phase with the waves that are produced earlier, such a situation is called the resonance condition. Instead of fixing the length of the string to be L equal to n lambda by 2, we could also change the frequencies of the tuning fork, to ensure that lambda of the waves produced by the tuning fork changes such that L equal to n lambda by 2, right? That is, the length will be the length of the string. We won't interfere with it, we won't make it equal to n lambda by 2, but we can change the frequency of the tuning fork so that the lambda, the wavelength of the waves created by the tuning fork, are such that lambda is equal to 2L divided by n, or L equal to n lambda by 2. And in that case, the frequency required by the tuning fork for this resonance will be F equal to Nv by 2L. Because as you can see here, if L equal to n lambda by 2, then lambda produced by the tuning fork can be replaced by V by F. And when you take F on the left side, you get F equal to Nv by 2L. Now, as you can see, this is the same frequency that we saw earlier. When I say F equal to Nv by 2L, what I really mean is that if the tuning fork vibrates with a frequency equal to Nv by 2L, where n is any integer 1, 2, 3, 4, in that case, the wave that comes back after reflection, when it goes from this end to this end and then it comes back from this end, the wave that comes back has a phase difference of n lambda with the wave that comes next from the tuning fork. We can make a general statement, and the statement is that resonance is achieved between any two vibrations when the frequency one vibration is equal to the natural frequency of vibration of the other vibration. So we can say that resonance is achieved between two objects when the vibration frequency in one object is equal to the natural frequency of vibration in another object. Here, one object is the tuning fork and the other object is the string. Resonance is achieved when the frequency of vibration of the tuning fork is equal to the natural frequency of vibration of the string, and we know that the natural frequencies of vibration of the string are given by F equal to Nv by 2L. So resonance is achieved when the tuning fork vibrates such that its frequency is Nv by 2N. Understood? Lot of concepts come in. Now let's apply these concepts by solving an IIT-JEE problem. Here it is. An object of specific gravity ρ is hung from a thin steel wire. The fundamental frequency for transverse standing waves in the wire is 300 Hz. The object is immersed in water so that one half of its volume is submerged. What will be the new fundamental frequency in terms of the original frequency? Now we already know that in case of standing waves in a wire or string, a string which is fixed at both ends, the fundamental frequency is V by 2L. We've already derived that. This string is hung, so definitely it must be fixed from the top. It has an object at its end because an object is hung from a thin steel wire. So the string must be fixed at the bottom too. It will be something like this. What we have to find out is the new fundamental frequency when one half of this object is immersed in water. And we have to find that new fundamental frequency in terms of the original frequency. So let's do this. Let's calculate the fundamental frequency in both cases, and then we can compare both of them. This is the string and the object when there is no water at all. The object is simply hanging from the string. In this case, the fundamental frequency will be V by 2L, where L will represent the length of the string. What will V be? V is the velocity with which waves can travel in this string. We know that in case of a string, the velocity is given by V equal to root T by mu. T is the tension in the string and mu is the mass per unit length in the string. We can calculate the tension in the string by balancing the force on this object. As you can see, the tension T acts upwards and the mass mg acts downwards. So clearly the tension T is equal to mg, and since the density of the object is given, we can say that density into volume is mass, or the tension in the string is rho v into g. So clearly the frequency will be square root of T by mu divided by 2L. Now we also know that mu equal to m by L. After all, mu is the mass per unit length, and since mass is rho v, density into volume, mu is equal to rho v divided by L. When we substitute mu equal to rho v by L here, and when we substitute tension equal to rho vg here, we get the fundamental frequency of vibration of the string in this case as 1 by 2L into root gl. Now what will be the fundamental frequency when half of this object is immersed in water? Let's see. As you can see, in this case, half of the object is immersed in water. In this case, if we balance the forces on this object, we'll see that a buoyant force will be acting on the object. This buoyant force will be equal to the density of the water into the volume of water displaced by the object to g. Since half of the volume of the object is immersed in water, the volume of water displaced will be V divided by 2, that is the volume of the object divided by 2. So the net force, the net buoyant force acting upwards will be density of water into V by 2 into g. In this case too, the fundamental frequency will be V by 2L. L is fixed, but what is V? V is square root of T divided by mu. Mu, the mass per unit length, will still be the same, but tension will change here. If we balance the forces here, we get T equal to mg minus rho water into V into g by 2, that is, the tension in the string is equal to the weight of the object minus the buoyant force acting on the object. On simplification and substituting rho V for m, we get the tension equal to rho minus half into Vg by 2. I have substituted the density of water here by 1 because the specific gravity of water is 1, and rho here represents the specific gravity of the object. So the tension is rho minus half into Vg by 2. Again, the fundamental frequency is square root of T by mu divided by 2L. If we substitute the value of tension here, and if we substitute mu equal to mass per unit length, that is rho Vg divided by L, we get the value of fundamental frequency as 1 by 2L into square root of rho minus half into GL by rho, a complicated term. Now we have to express this fundamental frequency in terms of the first fundamental frequency. If we take a ratio of the fundamental frequencies, we get F2 by F1 is square root of 2 rho minus rho water divided by 2 rho. In the question, it is given that the first fundamental frequency F1 is 300 Hz. Therefore, the second fundamental frequency will be 300 into square root of 2 rho minus rho water divided by 2 rho. That's the answer. All we did in this case was assume that the fundamental frequency in case of a string fixed at both ends is V by 2L. So that brings us to the end of standing waves in a string. Here, this animation about the vibration of a string will make you clearly visualize how a string's frequency varies. This is the first harmonic here in front of you. This is the first overtone. This is the second overtone. And this is the third overtone or the fourth harmonic. As you can see, the frequency in each case is different. The frequency is increasing, it's 1V by 2L in the first case, 2V by 2L in the second case, that is double the first case, 3V by 2L in case of the third harmonic, and 4V by 2L in the case of the fourth harmonic. Here you go, all the harmonics at once. Now let's take a look at another instrument called the organ pipe. Do you know what an organ pipe is? It's simply a pipe either open at both ends or closed at one end. An open organ pipe is a pipe open at both ends. A closed organ pipe is a pipe closed at one end. If you speak at this end here at the open end of the organ pipe, or if you generate sound waves here, wave will look like this, and it will get reflected from the closed end or from the open end. Then standing waves will be generated in the organ pipe. Now we want to know the condition that these standing waves must satisfy. For example, in case of a fixed string, we saw that only frequencies V by 2L will generate standing waves in a string. So we want to know what frequencies in this case required to generate standing waves. Are there any conditions? Like in the string there were nodes at both ends. So what are the conditions here? So as I just explained, when you make a sound here or when you sound a tuning fork here, sound waves are generated like this. Compressions, rarefactions, are generated. And just as in the case of ordinary longitudinal waves, you can say that a wave y equal to a cos kx minus omega t is generated. This wave gets reflected back again. Now we had studied case of longitudinal waves, also define a pressure amplitude. The pressure also changes along with the displacement of the particles. We had discussed this earlier. So when there is a compression, there is high pressure. When there is a rarefaction, low difference in pressure. So delta P, the pressure change at any point along the wave, also changes. And we had also discussed that this pressure change is at a phase angle pi by 2 compared to the displacement change. I know you might have forgotten, then I'll remind you. Delta P equal to P max sin kx minus omega t. Why sin? Because displacement is cos. And P max, remember we studied that P max was equal to BAK, where B was the bulk modulus, A was the amplitude of vibration of the wave, this A, and K was 2 pi by lambda. Even if you have forgotten, you can refer back to that chapter again. But essentially the pressure change at any point in a longitudinal wave is given by delta p equal to p max sine kx minus omega t. And the interesting point is, just as the actual wave y equal to a cos kx minus omega t, comes down and gets reflected back and forms a standing wave, this wave, the pressure wave, also forms a standing wave. This pressure wave also travels downwards and gets reflected back upwards and forms a standing wave. Let's see how. First, you see the displacement wave, y equal to a sine kx minus omega t, goes down. It becomes a sine kx plus omega t when it goes up, or when it gets reflected back. This is because this fixed end in a closed organ pipe is the rigid end, and so there's a phase change of pi when the wave gets reflected from this rigid end, because we've already studied that when a wave gets reflected from a fixed end, phase changes by pi. Similarly, in case of the pressure wave, if the pressure wave is at 90 degrees with the initial displacement wave, it will be delta p equal to p cos kx minus omega t. And similarly, the returning wave, the reflected wave in case of pressure, will be minus p max cos kx plus omega t. The plus sign is there because the wave is in the opposite direction, and the minus sign is there to account for the phase change of pi. In case of the displacement wave, the equation of the standing wave will be 2a cos kx sin omega t. I have simply added up these equations, y1 plus y2. And in case of the pressure wave, the equation will be 2p max sin kx sin omega t. Again, I have simply added up these two equations. So the net amplitude at any point for the displacement wave will be 2a cos kx, and the amplitude for the pressure wave at any point will be 2p max sin kx. So you can see that the amplitude of the displacement wave varies with cos kx, and the amplitude of the pressure wave varies with sin kx, given these equations of displacement and pressure. What are the limitations in this case, in case of a closed organ pipe? Like in the case of a string, we had said that both the ends are fixed, so both the ends must be nodes. Are there any limitations for this standing wave too? Yes, in case of a closed organ pipe, there are two limitations. The first limitation, of course, is that this end is fixed, and if this end is fixed, end of a standing wave must be a node, or only a node must fall here, like this. And since this will be a displacement node, it will be a pressure antinode. Why? Because we've just discussed that the pressure wave is at a phase difference of 90 degrees with the displacement wave. If you move on 90 degrees from a node, you get an antinode. After all, when you move on 360 degrees, you cover a distance lambda. So when you move 90 degrees, you cover a distance lambda by 4. And we know that a node and an antinode are separated by a distance lambda by 4. That is why a displacement node is always a pressure antinode, because both of them have a phase difference of 90 degrees between them. So that is one constraint. What is the other constraint? This point here represents a pressure node. Why? Because the pressure here will always be equal to the atmospheric pressure. Now you see, whenever we talked about a pressure wave, we always used the term delta P. For example, here we talked about the equation for delta P. The pressure wave represents the change in pressure at any point in the wave. Note that it doesn't represent the pressure at any point. It represents the change in pressure at any point because of the formation of the wave. We know that the change in pressure here is 0, because the pressure here is a constant, always equal to the atmospheric pressure, and that is the reason that this point is called a pressure node. And since it is a pressure node, it will be a displacement antinode. Why? Because we already know that the displacement and pressure are at phase difference of 90 degrees with each other. Now let's see what will be the simplest standing wave that can be formed here in this closed organ pipe. The simplest standing wave that can be formed will have a displacement antinode here, and it will have a displacement node here. So what will be the simplest that can be formed with a pressure node here and a pressure antinode here? I am talking about the pressure wave here. So the simplest pressure wave that can be formed with a node here and an antinode here is this one here. That's it. There is a node here because of the atmospheric pressure, there's an antinode here because of the displacement node, and this is your wave. Know that the distance between a node and an antinode is lambda by 4. So in this case, L, the length of the organ pipe, will be equal to lambda by 4. The frequency of vibration required to form this particular waveform is called the fundamental frequency or the first harmonic. In case of a closed organ pipe, when the fundamental frequency is there, L is equal to lambda by 4. But we can substitute lambda by V by F, and we get F is equal to V by 4L. So F equal to V by 4L is the fundamental frequency or the first harmonic in case of a closed organ pipe, because frequency generates the most basic waveform that can be generated in a closed organ pipe. This was of course a pressure wave that we were talking about. What will be the basic displacement wave that can be generated in a closed organ pipe? This one, because there's a displacement antinode here and there's a displacement node here. Therefore, this will be the fundamental frequency or the first harmonic that will be generated in case of a displacement wave. Again, as we know, L is lambda by 4 and the frequency will still be equal to V by 4L. So we just saw both the waveforms generated by a pressure wave and a displacement wave. Now what will be the next possible frequency that will generate a sustainable waveform in this closed organ pipe? Well, clearly the next frequency possible will have another node in the middle. So here, this will be the waveform generated in case of the second harmonic in a closed organ pipe. There will be one single node here, right? We are talking about the pressure wave here. As you can see, there is a pressure node here because of the atmospheric pressure. There is a pressure antinode here because of the fixed end displacement node, and we've generated an extra node here. So in this case, since the distance between two nodes is lambda by 2, this distance will be lambda by 2. And since the distance between a node and an antinode is lambda by 4, this will be lambda by 4. The length L will be equal to 3 lambda by 4. And by putting lambda equal to V by F, we get the second harmonic or the first overtone as F equal to 3V by 4L. So in the fundamental frequency here was F equal to V by 4L, and the second harmonic is F equal to 3V by 4L. Similarly, we can create the next possible waveform in case of a displacement wave. Next basic waveform formed in case of a displacement wave. In this case again, this will be a displacement antinode because this is a pressure node because of the atmospheric pressure. This will be a displacement node because this end is fixed, and we've generated another node in between. So again, in this case, we can again say that these lengths are lambda by 4 and lambda by 2. The net length is 3 lambda by 4, and the second harmonic will be 3V by 4L. What will be the next possible waveform that can be generated in case of a pressure wave? This one. As you can see, we've just created another node. So this is a pressure node. We always knew that because this is atmospheric pressure. So delta P is 0. This is a pressure antinode because this is a displacement node. So we've added this extra waveform here. Node, antinode, node, antinode, node, antinode. These distances are lambda by 2, lambda by 2 and lambda by 4, or the net length is equal to 5 lambda by 4, which simply means that the third harmonic frequency is F equal to 5V by 4L, the second overtone or the third harmonic. We can draw similar waveforms in case of the displacement wave, like this. Again, the displacement here is 0, so this is a node. The displacement here is maximum because the delta P here is minimum, so this is a displacement antinode. Again, these will be the lengths of the waveforms. L will be equal to 5 lambda by 4, and this third harmonic will be equal to 5V by 4L. So if we look at the frequency in each case resulting in a harmonic, we see that the frequency is 2n plus 1 V by 4L. For example, when you put n equal to 0, we get V by 4L. When you put n equal to 1, we get 3V by 4L. When we put n equal to 3, we get 5V by 4L. So you can see that any odd number, if you put an odd number here and multiply it by V by 4L, that will give you the frequency at which standing waves will be created in a closed organ pipe. I can repeat that there are two constraints in case of a closed organ pipe. One constraint is the closed end, where the displacement has to be 0, and the other constraint is the open end, where the pressure change has to be 0. You can remember this equation, F equal to 2n plus 1 into V by 4L in case of a closed organ pipe. This is the range of permitted frequencies in case of a closed organ pipe. An interesting phenomenon here is that just the condition of resonance in case of a fixed string was that the tuning fork or the external object you bring must be vibrating at the natural frequency of the string. Similarly, in this case too, the condition of resonance is that the tuning fork you bring or the external object you bring should be vibrating at one of these natural frequencies, because these are the natural frequencies of a closed organ pipe. Now let's have a look at an open organ pipe. Here it is. What will be the conditions in this case? Any limiting conditions which will limit the number of frequencies in an open organ pipe? Well, yes. You see, we already know that at any open end, the change in pressure has to be 0, because the pressure will be equal to the atmospheric pressure. So, this end will be a pressure node, and this end will also be a pressure node in case of an open organ pipe, because the pressure here and here will be constant, equal to the atmospheric pressure, delta P0, delta P0. And clearly, pressure nodes will always be displacement antinodes. So therefore, our only condition here is that both the ends will be pressure nodes and displacement antinodes. So what will be the fundamental frequency in this case? What will be the fundamental waveform of the standing wave that will be formed in this case? All we have to do is create a node here and a node here, and we can form a waveform, this one. So this will be the fundamental waveform in case of an open organ pipe. As you can see, the length of the pipe L will be equal to lambda by 2, since the distance between two nodes is always lambda by 2. If you substitute lambda by V by F, you get F equal to V by 2L. So the fundamental frequency in case of an open organ pipe is V by 2L, or the first harmonic in case of an open organ pipe is V by 2L. This will be the second case when you can put, this will be the next possible set of waveforms which standing waves can assume in an open organ pipe. As you can see, all we've done is added another node, and in this case this length will be lambda by 2 and this length will also be lambda by 2, because node distance is lambda by 2. Thus L will be equal to 2 into lambda by 2, or if we substitute lambda by V by F, we get F equal to 2V by 2L. So the second possible frequency in case of an open organ pipe will be 2V by 2L. This frequency will be the first overtone or the second harmonic. What will be the next possible frequency? The next possible frequency will exist when there are three such waveforms, that is when another node is created here. What we can conclude, however, is that in case of an open organ pipe, F equal to NV by 2L. Just as we sketched the waveforms in case of a pressure wave, we can sketch the waveforms in case of a displacement wave for a standing wave created in an open organ pipe, and again we'll still get the range of frequencies to be equal to NV by 2L. The condition for resonance is also F equal to NV by 2L. This means that if we bring a tuning fork or any object vibrating at a frequency equal to NV by 2L, then there will be resonance, because these frequencies here represented by NV by 2L represent the natural frequencies of the open organ pipe. Now let's have a look at all the three objects that we've studied at once. The range of possible frequencies, natural frequencies that can be created in a fixed string is NV by 2L. The range of possible frequencies that will generate a standing wave in a closed organ pipe is 2n plus 1 V by 4L, where 2n plus 1 represents any odd number. Similarly, the frequency that must be applied in an open organ pipe to generate standing waves is NV by 2L. In all these cases, the standing waves generated follow certain conditions, so that certain points are nodes and certain points are antinodes. You can see in this case, this point and this point are all pressure nodes, because in any organ pipe the open end will always have delta P equal to 0. This point is a displacement node, this point is a displacement node, and this point is a displacement node. So there you go. In case of organ pipes, we also have a special factor called the end correction. In case of the closed organ pipe, the length we use in writing V by 4L or 3V by 4L, you know, the L in L there is not exactly the length of the tube in real life. It is approximately equal to L plus 0.6 times the radius of the tube. Why? This is because of the inertia of the medium, the antinode, for example, you know that there's a pressure node here and a displacement antinode here. The displacement antinode is not exactly formed here at y equal to 0. It's formed somewhere above, you know, this opening because of the inertia of the medium. Similarly, in case of an open organ pipe, the antinodes, there is a displacement antinode here, there is a displacement antinode here. Both these antinodes are formed slightly outside the length of the open organ pipe. So whenever you consider the length in case of a closed organ pipe, you will consider L effective equal to L plus 0.6 times the radius of the organ pipe, if the radius of the organ pipe is given. Similarly, in case of an open organ pipe, you will consider the net length in V by 2L or in 2V by 2L, 3V by 2L, you will consider the length to be L plus 1.2 times the radius of the organ pipe. Why 1.2 times? Because 0.6 times the length will increase here and 0.6 times the length will increase here. So 0.6 plus 0.6, 1.2 times the radius of the pipe. Now that we've studied enough theory, again let's try to attempt an IIT-JEE problem. The air column in a pipe closed at one end is made to vibrate in its second overtone by a tuning fork of frequency 440 Hz. That is simple enough. The speed of sound in air is 330 meters per second. Ignore end corrections. Assume P0 to be the mean pressure at any point in the pipe and assume delta P0 to be the maximum amplitude of pressure variation. Find the length of the air column L, the amplitude of pressure variation at the middle of the column, the maximum and minimum pressures at both the ends of the tube. First part of the question is simple. That there is a closed organ pipe, we know that it is vibrating in its second overtone, that is like this. We are given the frequency to be f equal to 440 Hz in this case, and we already know that in case of a closed organ pipe, in this case the frequency is 5V by 4L. Even if you didn't remember that the frequency was 5V by 4L, you would clearly know that in case of the second overtone or the third harmonic, there would be two notes in the middle. So when you would draw this diagram, you could clearly see that this length is lambda by 2, this length is lambda by 2, this length is lambda by 4. You add all that, equate it to L, and then substitute lambda by V by F. You can derive the expression yourself during the exam. So the frequency in this case is 5V by 4L or 440 Hz. V is given because V is the velocity of sound. So you can easily calculate the length of the closed organ pipe, which is equal to 15 by 16 meters here. The second part of the question is slightly tougher. Second part involves calculating the change in pressure at exactly the middle of this pipe. So if this is x equal to 0 and this is x equal to L, then the second part involved calculating the change in pressure at the middle point x equal to L by 2. Now we know that the amplitude of pressure change at any point x in the pipe is equal to delta P naught sine kx. We had already calculated that. Delta P naught here represents the maximum possible pressure change. Clearly delta P is delta P naught sine kx. Now we have to calculate delta P at x equal to L by 2. So let's put L by 2 here. We know that k is 2 pi divided by lambda. So delta P is delta P naught sine 2 pi by lambda into 5 lambda by 8. Where did 5 lambda by 8 come from? I have substituted L here by 5 lambda by 4. And when I did that, L by 2 became 5 lambda by 8. That is why x equal to L by 2 here has become x equal to 5 lambda by 8 here. After simplifying, we get delta P is plus minus delta P naught divided by root 2. So that will be the value of the change in pressure here in the middle of the closed organ pipe. The third part of the question is even more interesting. We have to calculate the exact values of maximum and minimum pressure at both the ends of the closed organ pipe. That is, we have to calculate the maximum and minimum pressure at this end, the open end, and the maximum and minimum pressure at this end, the closed end. We know that delta P is 0 at the open end of a closed organ pipe. Why? Because as we know, the pressure here is constant, equal to the atmospheric pressure. So clearly the maximum pressure or the minimum pressure or any other pressure here will simply be equal to the atmospheric pressure. One part of the question is solved. Now we also know that the pressure difference at the closed end of a closed organ pipe is maximum because there is a pressure antinode here. So this place will have delta P maximum. And we know that the maximum value of delta P is clearly delta P naught, the amplitude of pressure variation, right? And if delta P is delta P naught, clearly the maximum pressure at this end will be the average pressure given, the mean pressure given, plus delta P naught, and the minimum pressure at this end will be the average or mean pressure given minus delta P naught. So some concepts, some basic reasoning, and there you go, this IIT problem has been solved. Now let us learn about some devices which make use of standing waves to achieve a certain purpose. For example, Kundt's tube is a device which makes use of standing waves to compare the velocities of sound in a solid and a fluid. How does it do this? As you can see, a Kundt's tube consists of a box like this. At the edge of the box is a piston here and a piston here. Very near this box is a small clamp and a rod is clamped at its midpoint like this. This rod is free to move at both ends. Like maybe when you look at this rod, you will feel that this rod is attached to this piston. But no, that is not the case. This rod is free to move here and here. It's just very near this piston. This rod contains the material whose speed has to be ascertained, the solid material. This box contains the fluid whose speed has to be ascertained. So the Kundt's tube will give us the ratio of the speed of sound in this material, this solid, and this fluid. This box is also lined with a special kind of powder called lycopodium powder. This is the fluid, as I just told you. This is the solid. And this is the clamp, the fixed clamp. Now in a Kundt's tube, this rod is gently vibrated. When that happens, standing waves are generated in the rod. This is because when you vibrate this rod at this end, a a wave travels to this end, then it comes back to this end and standing waves are generated. However, standing waves are generated in such a way that there is a node at the clamp. After all, this end is free to move, this end is free to move, and there is a node here. So the basic waveform that will be formed is like this: an antinode here, a node here, and an antinode here. The vibrations in this rod cause the fluid here to vibrate with an equal frequency. When the fluid here vibrates with exactly the same frequency as this rod, nodes and antinodes are created inside the fluid. A wave travels like this, and then it gets reflected back like this to create standing waves. Again, this end is fixed and is a node, this end is fixed and is a node. At the place where nodes are formed, the lycopodium powder gets deposited. This is because at the nodes there is zero displacement, unlike in the other places where there is at least some displacement. Now if you take a gas like air, when there is displacement in the medium, the lycopodium powder particles will be scattered here and there. They will not settle down. They will be moving all around the place. But when the displacement of the medium is zero, when the displacement of the air or gas or the fluid we want is zero, then the lycopodium particles will not move. They will settle down like this. So at all the nodes, the lycopodium particles settle down. In fact, the distance between two heaps of lycopodium particles will definitely be lambda f by 2. That is the wavelength in the fluid divided by 2, because the distance between two nodes is lambda by 2. Similarly, here you can see that the distance between two antinodes is lambda s by 2. That is lambda solid divided by 2. Based on these two values of wavelengths of the standing waves created in the fluid and in the solid, we can easily calculate the velocity of sound in the solid divided by the velocity of sound in the fluid. We can do this because we know that the frequency of vibrations here and here is just the same, and frequency can be written as V divided by lambda. Therefore, since the frequencies here and here are same, Vf divided by lambda f is equal to Vs divided by lambda s. That is, the velocity of sound in the fluid divided by the wavelength of the standing waves in the fluid is equal to the velocity of sounds in the solid divided by the wavelength of sound in the solid. When we do this, we get the ratio Vs by Vf, which is what we require, the velocity of sound in the solid divided by the velocity of sound in the fluid. That was simple, wasn't it? Now let's study Quincke's tube. Quincke's tube is a device used to determine the velocity of sound in a fluid. Quincke's tube, unlike the other devices, does not make use of the phenomenon of stationary waves. It simply makes use of the phenomenon of interference. But still, we'll study it here because it will help us explore the phenomena of constructive interference in an even better way. Quincke's tube, as you can see, consists of two U-tubes, this one and this one. One of the U-tubes is slightly smaller than the other U-tubes so that it fits into the other U-tube. At one end of the Quincke's tube is a candle, and on the other end there is a tuning fork set at a certain frequency. When the tuning fork is sounded, waves are generated. One wave travels through this path like this, and the other wave travels through this path like this. The length of both the tubes is kept the same, so both the waves generated from the tuning fork come here at the same time after traveling the same distance. They meet at this point. Now we clearly know that if there are two waves which are completely in phase with each other, that is, which are taking the same time to cover the same distance, then both of them will definitely interfere constructively, right? For example, if this wave here is this and this wave here is this, then both of them at this point will interfere constructively to create a wave with a much larger amplitude. This is because both of them are traveling along the same path, so the phase difference between both of them is clearly zero. This constructive interference causes the candle to flicker a bit. After all, there is a disturbance created here because of the constructive interference. Constructive interference occurs when the length of the left side tube is the same as the length of the right side tube. Now, this tube here is moved slightly to the right. When that is done, the distance covered by one wave increases and the distance covered by the other wave here decreases. This is because we've moved this tube on the right towards the right. As we do so, a greater part of the tube on the left gets exposed. So, though the length of the right tube remains the same, the length of the left tube increases, and thus the length traversed by the wave on the left increases. Now, we know that if two waves interfere constructively, then their amplitudes must be in line with each other. In fact, every part of them must be in line with each other. Now, when will these waves interfere next? Obviously, after a path distance of lambda, right? Therefore, after one of the waves has travelled a distance lambda more than the other wave, they will interfere constructively again. By constructive interference, I simply mean that these waves will then again be in phase with each other. Therefore, when we move the right tube towards the right by a distance L, the wave on the left will have to travel a distance L plus L, that is 2L extra. Now we know that there will be constructive interference only when this length 2L, that is the extra distance travelled by the wave on the left, is equal to lambda, the wavelength of the wave. When that happens, the candle will flicker. So what we will do is, we will initially take down the reading when the candle flickers. When both the path lengths are equal, we'll again take out the reading when the candle flickers again. We'll move the tube on the right to the right until the candle starts flickering again. Once the candle starts flickering again, we'll note down the reading again. The difference in the reading here will be L, and we will know that since the candle is flickering again, constructive interference is taking place again. We know that the path difference between two constructive interferences is lambda, as we just saw. That is why 2L will be equal to lambda. But we already know that V is equal to F lambda. V is the velocity of sound. F is the frequency of the tuning fork, and lambda, as we just found out, was 2L. This helps us determine the velocity of sound in the fluid. Isn't that simple? It is. Now let's see how we can make use of a resonance tube, a device called a resonance tube, to determine the velocity of sound. This device is used to measure the velocity of sound using the phenomenon of stationary waves. As you can see, a resonance tube simply consists of a tube of water. However, the water level in this tube can be varied by means of a tank situated here. Now, we put a tuning fork very near the mouth of the resonance tube. When we start vibrating the tuning fork, the air column above the water starts vibrating. This air column here, as you can clearly see, behaves like a closed organ pipe. We slowly start decreasing the level of water in this tube. Now, we already know that the frequency, the fundamental frequency that can be created in a closed organ pipe is F equal to V by 4L. In the earlier case, the length of the closed organ pipe was constant while we were changing the frequency so that we could obtain the fundamental frequency in case of a closed organ pipe. In this case, the frequency of the tuning fork here is constant, so we already know the fundamental frequency that will be obtained in the closed organ pipe. But what will be the length of the closed organ pipe to give this fundamental frequency? That is what we are trying to obtain. So we are changing the length to obtain such a length that the basic waveform in case of a closed organ pipe will be created like this. Now, as soon as the length of the air column becomes equal to lambda by 4 or equal to 1/2 the length of a single waveform, resonance occurs. This is because the fundamental frequency of this closed organ pipe that has been created here becomes equal to the frequency of the tuning fork. Because of the resonance, a pop sound is heard. So we record the water level at which the pop sound is heard. Let us say this pop sound is heard when the water level is at length L. Now, there is also some distance between the top of the resonance tube and the tuning fork. The waveform will be formed right underneath the tuning fork. So this distance between the top of the resonance tube and the tuning fork must also be taken into account. So lambda by 4 is equal to L plus E, because the distance from here to here is clearly lambda by 4. Now we further decrease the water level like this. Finally, we keep decreasing the level until another pop is heard. When will another pop sound be heard? Of course, when another possible frequency in this closed organ pipe will be generated. As you can see, this is the next possible waveform that will lead to resonance with the tuning fork. Therefore, a pop sound is heard when this waveform is created. After all, the frequency of the tuning fork has become equal to the second harmonic frequency of this closed organ pipe. Now, this length is clearly 3 lambda by 4. And, as in the previous case, L1, the new reading of the air column, plus E is equal to 3 lambda by 4. By using the formulae L plus E equal to lambda by 4 and L1 plus E equal to 3 lambda by 4, the values of E and lambda can be obtained. Now, since the frequency of the tuning fork, which is the same as the frequency of vibration inside the closed organ pipe, is known, lambda is known, the velocity of sound V can easily be calculated by using the formula V equal to F lambda. This is how a resonance tube is used to calculate the velocity of sound. I know this seems a bit complicated. Therefore, you can go back and rewind the video, watch it closely again, and slowly your concepts will become very clear. Let's move on to the next topic we have, beats. Beats are produced when two waves with different angular frequencies and different wavelengths interact with each other, such that the angular frequencies of these two waves are very near each other. You've already heard of the term beats, right? Dhak dhak, dhak dhak. Those are beats. Now let's see how these beats are produced. You see, we already know that if there is a wave y1 equal to a sine omega 1 t minus k1x, and if y2 is a sine omega 2 t minus k2x, then when these two waves interact, this is the wave that will be produced, y1 plus y2. If we further simplify this expression by using the formula sine a plus sine b is equal to sine a plus b by 2 cos a minus b by 2, this is what we get. Now we can clearly see that this part of this expression can be considered to be the amplitude of the wave, a varying amplitude, and this part can be considered to be omega dash, and this part can be considered to be k dash. So you see, this wave, as we had already studied in the previous chapter, represents a wave, a normal wave of the form a sine omega t minus kx, where the amplitude is varying as a cosine function. If we took a snapshot of this wave, this is how it would be. As you can see, the amplitude changes as a cosine function. This is the equation of a normal wave. You see, a normal wave, it just goes on. However, the amplitude decreases, increases, decreases and increases. This is where the phenomenon of beats comes in. If this kind of wave is created in the atmosphere, you'll hear a beat every time the amplitude of this particular wave combination is the maximum. So for example, whenever the magnitude of the amplitude becomes a1 plus a2, that is the sum of the amplitudes of both the waves, then that's when you hear a beat. So duk, a beat is heard, duk, a beat is heard again. So whenever the maximum amplitude derived by the combination of both the waves that constituted it is reached, a beat is heard. This beat is heard because both the waves are constructively interfering at that time, and the final amplitude is actually a1 plus a2 at that time. Now, is this frequency called beat frequency? What is beat frequency? It is the number of times you hear a beat in 1 second. Duk duk, duk duk. How many times is that happening in 1 second? So now let's calculate the beat frequency. We know that intensity for any wave on this earth is proportional to the square of its amplitude. So in this case, the intensity of this wave combination is proportional to the square of its amplitude right here. Now if we carefully consider the value of k1 minus k2, we can neglect k1 minus k2. Why? Because we've already discussed that omega 1 is very near omega 2. I had already mentioned that. And if that is so, k1 is even nearer to k2 because k is omega divided by v. So if omega 1 minus omega 2 is a small number, then omega 1 minus omega 2 divided by v is what k1 minus k2 is, and that's an even smaller number. So we can safely neglect k1 minus k2. When we do that, we get intensities approximately proportional to cos square omega 1 minus omega 2 t by 2. Now we can use the identity 2 cos square theta equal to 1 plus cos 2 theta, and therefore we can simplify this expression to this. We can see that intensity clearly depends on the difference of the angular frequencies. When we hear a beat, what is it that we are really hearing? We are hearing an expression of the highest possible intensity of the waveform that has been created by the combination of the two waves. So since we have seen that omega 1 minus omega 2, the difference of angular frequencies varies linearly with the intensity, we define beat frequency as omega 1 minus omega 2 divided by 2 pi equal to f1 minus f2. Thus the beat frequency, the frequency of intensity increasing and decreasing. It is number of times the intensity reaches its maximum value in 1 second. It is also the number of times the maximum value of amplitude equal to a1 plus a2 is attained in 1 second. The beat frequency is also equal to 1 by t, where t is the time between two increases in intensity. So well, we've had enough of theory for a long time. Let's go back to solving what we really love doing, IIT-JEE problems. A vibrating string of length L under a tension T resonates with a mode corresponding to the second harmonic of an air column of length 75 cm inside a tube closed at one end. The string also generates 4 beats per second when excited along with a tuning fork of frequency n. Now the number of beats gets reduced to 2 per second. Assuming the velocity of sound in air to be 340 meters per second, calculate the frequency n of the tuning fork. The language of this problem seems very complicated. However, this question is actually a very simple one. It talks about closed organ pipes, it talks about tuning forks, it even talks about a string. So what's happening? What the question says is, initially a closed organ pipe vibrating in its second harmonic frequency is in resonance with a string here. Now we know that the frequency of a closed organ pipe is 3V by 4L, and since both these objects are in resonance with each other, the frequency of vibration of the string must also be equal to 3V by 4L. Now the question says that there is a tuning fork here which produces 4 beats with this string. Now that clearly means that the difference in the frequencies of the string and the tuning fork is 4 Hz. We have to find out the frequency of the tuning fork. Sounds simple enough, right? The frequency of the string is given because L is the length of the closed organ pipe, which is given. V is the velocity of sound, which is given. So clearly 3V by 4L can be obtained. Since the tuning fork has a frequency difference of 4 Hz from the string, its frequency will either be 3V by 4L plus 4 or 3V by 4L minus 4. Now when the tension in the string is increased, the beats produced decrease to 2. This means that when we increase the tension in the string, that is when we increase the velocity in the string, because velocity is proportional to root t, the number of beats decreases to 2. So when we increase the frequency of this string, the number of beats decreases to 2. Definitely, that means that the frequency of the tuning fork is greater than the frequency of the string. This is because when we are increasing the frequency of the string by increasing the tension in the string, the frequency difference is decreasing. Therefore, since the frequency of the tuning fork is greater than that of the string, the frequency of the tuning fork is clearly 3V by 4L plus 4. Substituting the values of V given, L, the length of the closed organ pipe that is given, we get the frequency of the fork to be 344 Hz. So you see, the problem which sounded very complicated was actually very simple. One thing you must be careful about in this problem is that L is not the length of the string in this case. It is the length of the closed organ pipe. You may also be thinking, how can a string vibrate with a frequency 3V by 4L? We already know that it can only vibrate with a frequency V by 2L or 2V by 2L or 3V by 2L or NV by 2L. Where did 3V by 4L come from? This is possible here because L here is not the length of the string. L in 3V by 4L is equal to the length of the closed organ pipe. So you cannot compare this to NV by 2L, where L is equal to the length of the string. Got it? Now let's solve another IIT problem. Here, this question was asked in IIT-JEE 1993 and will definitely clear your concepts about beats. Two radio stations broadcast their programs at the same amplitude A and at slightly different frequencies omega 1 and omega 2 respectively, where omega 1 minus omega 2 is 1000 Hz. A detector receives the signals simultaneously. It can only detect signals of intensity greater than or equal to 2A square. Find the time interval between successive maxima of the intensity of the signal received by the detector. Also find the time for which the detector remains idle for each cycle of the signal. At first glance, this problem seems quite fuzzy. What is happening here? There are these two radio stations, radio station 1 and radio station 2. Both of them are emitting signals. The equation of the signal emitted by the first radio transmitter is y equal to a sine omega 1t minus kx. The equation of the second signal is y equal to a sine omega 2t minus kx. The amplitudes of these signals is the same. Omega 1 and omega 2 are such that omega 1 minus omega 2 is small value given to be 1000 Hz. Since omega 1 and omega 2 is given to be small, we can definitely assume that k1 minus k2 is so small that we can almost assume k1 equal to k2, which is why I've written k in both cases here. Now what's the question? The question is, what is the time difference between two intensity maxima obtained by the interaction between these two waves? You see, this wave will interact with this wave. The intensity, the resultant intensity will vary, it will go up, it will go down. So what is the time difference between two maxima of that intensity? That's what we have to find out. F1 minus F2, as we already know, is the beat frequency. And the beat frequency is equal to the number of times the intensity becomes maximum in 1 second. So therefore, clearly, 1 by F1 minus F2 is the time gap between two intensity maxima. F1 is given to be 1000 divided by 2 pi. Thus, the final time period between two intensity maxima is t equal to 2 pi divided by omega 1 minus omega 2. That is 6.28 into 10 raised to minus 3 seconds. Now the idle time is the time when the intensity is less than 2a square. Why? Because the detector can only detect frequencies greater than or equal to 2a square. Since intensity is proportional to the square of the amplitude, this will happen when the amplitude varies between minus root 2a and plus root 2a. Now what is the amplitude? When we combine the equations of the two waves that we saw in the previous screen, we get this equation. We've seen this equation already many times. As you can see, this here is the amplitude of this wave, and this here is the ordinary wave. And as you already know, the amplitude increases and decreases as a cosine function. Now we want this amplitude here to be between minus root 2a and plus root 2a. Therefore, when we substitute the value of amplitude by this function, is what we get. Thus, the final time period between to intensity maxima is t equal to 2 pi divided by omega 1 minus omega 2, that is 6.28 into 10 raised to minus 3 seconds. Thus, if we simplify this expression, we get minus 1 by root 2 less than cos 500t less than 1 by root 2. Using mathematics, we can prove that the value of the cosine function lies between minus 1 by root 2 and 1 by root 2 between these regions indicated by red in one time period. If we further use mathematics, we get pi by 4 less than 500t less than 3 pi by 4 right here, and we get 5 pi by 4 less than 500t less than 7 pi by 4. So the detector will be idle twice in one cycle, as we can clearly see. When we add these times for which the detector will be idle, we get the idle time to be 6.8 into 10 raised to minus 3 seconds. There you go. Now we are going to study a fascinating phenomena called Doppler effect. The IITs are known to be so fascinated by the Doppler effect that every few years there is an intense question regarding this topic. What is the Doppler effect? According to the Doppler effect, if there is a source emitting a certain wave at a certain frequency, the observer will detect a different frequency than the frequency emitted if he is moving, and the observer will detect a different frequency than the frequency emitted if the source is moving. So if either of source or observer are moving, then the frequency detected by the observer will be different from the frequency emitted by the source. Practically, we can understand this by visualizing the situation when a truck is approaching us. When the truck is far away, the frequency of the horn that we hear is much different from the frequency of the horn when the truck is right next to us. This is the Doppler effect. Similarly, if a man is shouting and running at the same time towards us, the frequency of his voice that we hear when he is a long distance away will be much different from the frequency that we hear when he is right next to us running. So let's see how this works. Now, what will be the frequency detected by the observer if he is moving with respect to the source? Let's find this out by looking at the core definition of frequency. What does frequency really mean? It is the number of waves received by the observer in 1 second, isn't it? All we have to do to calculate the frequency a moving observer will observe is calculate the number of waves he receives in 1 second. We can do that by calculating t dash, the time between two consecutive waves received by the observer. So for example, this is one wave and this is another wave, then the time taken by the observer to receive this wave completely, the time in which this wave passes through the observer completely and the next wave is just about to pass through the observer, that is the time between two consecutive waves received by the observer, equal to t dash. So the time taken by the wave to pass through the observer completely is t dash, and 1 by t dash the frequency experienced by the observer. So let's see what happens when the observer is moving. Let's take two time intervals, time t equal to 0 and time t equal to t dash. At time t equal to 0, we're starting the experiment. At time t equal to t dash, the observer will have completely received exactly one wave, right? So let's see what happens. Point B is the point where the observer receives one wave completely. So you see, at B, the observer has received one wave completely and is just about to receive the next wave. At this point, the net distance traveled by the second wave, the wave that he is just about to receive, is this. This distance is clearly equal to lambda plus AB. You see, at this instant, this second wave was at a distance lambda from the observer, and in time t dash, this second wave has traveled from here to the observer. So the net distance that this second wave has traveled is lambda plus AB here, isn't it? This means the distance traveled by the second wave which the observer hadn't received at time t equal to 0, which was after the wave the observer was receiving at time t equal to 0, the net distance traveled by that wave in time t dash is clearly lambda plus AB. However, the distance traveled by that wave is also speed into time, that is speed of the wave v into time t dash. So clearly v into t dash is lambda plus AB. But we know that the observer has a speed VO, and so the distance AB is clearly equal to VO into t dash. The distance AB is VO into t dash, speed of the observer into time. Lambda itself is equal to V into t, where t is the actual time period of the wave, isn't it? Lambda is V into t. Therefore, substituting V into t for lambda, we get the new time period as the time period that is detected by the observer as V into t divided by V minus VO. Inverting this equation, we get new frequency observed by the observer is F into V minus VO by V. Here V is the velocity of sound, or the velocity of the wave we are talking about, and VO is the velocity of the observer. You should remember this equation. What we have finally concluded is that if the observer is moving away from the wave source with a velocity equal to VO, then the frequency that he will detect is F into V minus VO by V, where F is the frequency emitted by the source. Now what will happen if the observer is moving towards the source? Let's derive an expression for the frequency that the observer will detect when he is moving towards the source. In this case too, let's assume that in time t dash, apparent time period, observer is moving from A to B in such a way that this one black wave will pass through him when he reaches B. So when he reaches B, he'll just start to receive the green wave. In t dash, the time period is the time in which one entire black wave will pass through the observer. Observer is moving to the left with a speed VO. He is moving towards the source. So let's start the time. You can clearly see that the net distance moved by the green wave in this case is lambda minus AB. Lambda minus AB is the net distance traveled by the wave. However, we already know that the distance traveled by the green wave is also equal to the speed of the green wave into taken t dash. Equating these two expressions, we get V into t dash is lambda minus AB. We already know that AB is the distance traveled by the observer in time t dash. So we can substitute AB by speed of the observer into time t dash. And we can similarly substitute lambda by speed of the wave into original time period of the wave, t. Simplifying as in the previous case, we get the frequency experienced by the observer is F into V plus VO divided by V in the case when the observer is moving towards the source with a speed VO. V here is the original speed of the wave, or the speed of sound in case of sound. Things get a bit more complicated when the source is moving. Let's have a look at what exactly happens as the source emits a wave. The source first emits a wave like this. After this wave the source has emitted has traveled a distance equal to lambda, the source emits another wave. So you can clearly see that as the wave it has first emitted has traveled a distance lambda, it emits another wave after a distance of lambda. Now let's see what happens when the source is moving. It first emits a wave, and after the wave has moved a distance lambda, this is what the situation is. The source has moved a distance d, the wave has moved a distance lambda, and apparently the distance between the source and the end of the wave is lambda minus d. So after a distance of lambda minus d from the end of the other wave, the source emits another wave. Again, the source has moved a distance d, the wave has moved a distance lambda, but as you can see, the difference between the two waves emitted is now lambda minus d. Earlier, a wave travelled a length lambda, and then another wave of length lambda was emitted, then another wave of length lambda was emitted. Now, after every distance lambda minus d, a new wave is being emitted. What this means is that this is what the observer will see. He will see that the distance between two crests or two troughs or two waves in general is lambda minus d, and so he will presume that the wavelength itself has changed to lambda minus d. Now when that happens, since d is the distance travelled by the source in one time period equal to velocity of the source into time, clearly the apparent wavelength that the observer observes is lambda minus Vs into t. To further simplify this equation, we can write the apparent wavelength as speed into the apparent time period. The speed of the wave does not change for the observer because he is at rest, he is not moving at all. So the speed he will see is simply the speed of the wave. So lambda dash, the apparent wavelength, can be written as speed into the new time period equal to v into t, is speed of the wave in reality into the actual time period minus the speed of the source into the time period. On inverting this equation and simplifying, we get the apparent frequency experienced by the observer is f into v divided by v minus vs, where f is the original frequency emitted by the source. The source in this case is moving towards the observer with a velocity equal to vs. When the source is moving away, by similar calculations, we can obtain the expression for the apparent frequency detected by the observer as f into v divided by v plus vs. In this case, vs, the speed with which the source is moving away from the observer. Now you see, observer is moving away, the observer is moving near the source is moving away, the source is coming nearer. So many formulas, so many equations. How to remember all this? Or do you have to derive it every time? There's an easy way to remember all this. That the apparent frequency detected by the observer is always f into v plus minus vo divided by v plus minus vs, where v, the velocity of sound or the wave received, vo is the velocity of the observer, and vs is the velocity of the source. If the observer is moving away, you will use v minus vo. If the observer is moving towards the source, you will use v plus vo. The opposite will be true in case of the source. If the source is moving towards the observer, you will use v minus vs, and if the source is moving away from the observer, you will use v plus vs. Also, in the case when both source and observer are moving, you can still use this equation. For example, if the observer is moving away and the source is moving towards the observer, then you will write v minus vo and v minus vs. It. Now let's move on towards some IIT-JEE problems yet again. This problem was asked in IIT-JEE 2003. A policeman moving at 22 meters per second chases a motorcyclist. The policeman sounds his horn at 176 Hz, while both of them move towards a stationary siren of frequency 165 Hz. Calculate the speed of the motorcyclist if he does not observe any beats, given that the speed of sound is 330 meters per second. So this problem combines the concepts of beats and Doppler effect. Let's see how to proceed. Here, this is the problem in pictorial form for you. A motorcyclist moving with a velocity v. This is the velocity v that you have to find out. A police car is moving behind him at a speed 22 meters per second and is emitting a frequency 176 Hz. A stationary siren is situated in front of the motorcyclist and it is emitting a frequency of 165 Hz. Now this motorcyclist does not hear any beats. Now we can clearly see that the frequencies emitted by the police car and the stationary siren are very close to each other. So in ordinary circumstances he should have heard beats. But if he does not hear beats, this means that the frequency observed by the motorcyclist coming from the police car and coming from the stationary siren is exactly the same. So the apparent frequency that the motorcyclist observes from the police car and the siren is just the same. So by using the Doppler effect, we can calculate the frequency that the motorcyclist will observe because of the police car. We can calculate the frequency that he will observe because of the stationary siren, and we can equate those two frequencies. So let's do it. The frequency because of the policeman will be F into V minus VO divided by V minus Vs. We've written V minus VO because observer, the motorcyclist in this case, is moving away from the source, the policeman in this case. We've written V minus Vs because the source, that is the policeman, is moving towards the observer, that is the motorcyclist. F, the frequency of the original waves emitted by the policeman, is given to be 176 Hz. After making the appropriate calculations, this is the expression that we obtain. Here we see the motorcyclist and the policeman. In case of F siren, the frequency emitted by the siren, the observer observes, use the formula F into V plus VO by V. We use V plus VO because in this case, as you can clearly see, the observer, that is the motorcyclist, is moving towards the source, that is the siren. At the bottom, we do not use any plus minus sign because the source, that is the siren, is not moving at all. Simplifying, we get this expression. When we equate this expression to this expression, we clearly get the value of VO, the velocity of the observer. This comes out to be 22 meters per second. So that's the answer. This problem was asked in IIT-JEE 2007. Let's see if you can solve it. Two trains A and B are moving with speeds 20 meters per second and 30 meters per second respectively in the same direction on the same straight track, with B ahead of A. The engines are at the front ends. The engine of the train A blows a long whistle. Assume that the sound of the whistle is composed of components varying in frequency from F1 equal to 800 Hz as shown to F2 equal to 1120 Hz as shown. The speed of the sound in air is 340 meters per second. What is the speed of sound of the whistle for passengers in A and B? What is the spread of frequency, highest frequency minus lowest frequency, observed by the passengers in train B? And which of the following best represents the distribution of sound intensity observed by the passengers in train A? This problem seriously seems so complicated. The point is, if you go beyond the words and just look at what's happening, it isn't tough at all. Here, the problem says that there are two trains, train A and train B, moving in the same direction and along the same track. Train A is moving right behind train A at 20 meters per second and train B is traveling at 30 meters per second. Now, train A blows a whistle, and this whistle is such that the frequencies vary between 800 to 1120 Hz. The first thing we have to calculate now is the speed of sound heard by passengers in train A and train B. That's the first question. Now if you look at the passengers in train A, the whistle has been blown here in the engine of train A. So sound is moving to the left towards the passengers at 340 meters per second. So if you assume that the passengers in train A are at rest, then relative to them, clearly the sound is moving at a speed 340 plus 20 meters per second, because the passengers in train A are moving to the right at a speed 20 meters per second. But if you want to relatively calculate by what speed the sound is moving towards the passengers, and then you assume the passengers at rest, you will see that the sound is definitely moving at 340 plus 20, 360 meters per second towards them. Similarly, for people in train B, the sound is coming from behind, because train A is behind train B, and therefore since train B, the passengers in train B are moving forward at 30 meters per second, they will clearly hear the sound coming towards them with a speed 340 minus 30 meters per second, that is 310 meters per second. These are simple concepts of relative velocity. So the velocity of sound for passengers in A is 360 meters per second, and for passengers in B it is 310 meters per second. The first part was fairly simple, just relative velocity. In the second part of the question, they are asking what is the frequency, what is in fact the spread of frequency observed by the passengers in train B. According to them, the spread of frequency is simply the difference between the highest frequency and the lowest frequency. So the second part of the question is, what is the frequency range observed by the passengers in train B, or in fact what is the difference in the highest and lowest frequencies observed by the passengers in train B. Now let's assume that this green ball here represents the passengers in train B. Where is the sound coming from? It's coming from the source here. The engine of train A is the source. So the engine of train A is the source behind train B, which is in front. We know that the passengers in train B are the observers traveling at 30 meters per second. The source, which is the engine of train A, is traveling at 20 meters per second. So we can clearly see that this velocity of the source in this case is 20 meters per second, and the velocity of the observer is 30 meters per second. So we clearly know from Doppler's effect that the frequency observed by any passenger in train B will be F into V minus V observer divided by V minus V source, where V is the velocity of sound, VO is the velocity of the passengers in train B, and Vs is the velocity of the source. Here I have assumed the minus sign in the numerator because the passengers in train B are moving away from the source, that is away from the engine of train A. I have observed a minus sign, I have put a minus sign in the denominator because the engine which is emitting the whistle is moving towards the observer. Been given the lowest and highest frequencies emitted by the whistle, 800 Hz and 1120 Hz. So putting f equal to 800 and 1120 Hz, we get the frequency spread, that is the difference between the highest f dash and the lowest f dash observed by the passengers in train B as 310 Hz. So all we used here was Doppler's effect. That's it. Then what was that third question about graphs? We were given 4 graphs representing the variation of intensity with the frequency range. This is the frequency range emitted by train A. The question was, what is the variation of the distribution of the sound intensity of the whistle as observed by the passengers in train A? Now clearly, for the passengers in train A, the engine which is emitting the sound is at rest. Therefore, there is no relative motion between the passengers of train A and the engine of train A which is emitting the sound. And since there is no relative motion at all, clearly the intensity, the frequency of vibrations of the sound heard by the passengers of the train A will be exactly the same as those emitted. For example, if the engine emits a frequency F1, the passengers of train A will hear or perceive F1. If the engine emits a frequency F2, the passengers of train A will perceive F2. This is because they are moving at the same velocity as the engine. So there is no relative velocity between the source and the observer in this case. The observer being the passengers of train A and the source being the engine of train A. This is the graph that represents the range of frequencies heard by the passengers of train A, because nothing has changed for them. as there is no relative velocity between the source and the observer. So this option is correct. So as you can see, Doppler's effect can be pretty easy. All you have to do is apply the core concepts and remember the formulae. When the source is moving, the observer is moving, and when both are moving. Until the next chapter, goodbye.